Alright, I'm just going to wing it here on this one. It's for you, Kirby, primarily. Okay, so here we have a cuboctahedron inside of a cube. And we also have rhombic faces and this long orange diagonal. This size of this combination of forms is that the long diagonal, orange, is going to be the length of 2, and it is an edge of an icosahedron. The icosahedron, which is 5 times the square root of 2 times phi to the second power tetrahedral units, that gets jitterbugged from the vector equilibrium of 20 units. And the rhombic face is the rhombic tricontahedron, of which there's 30. We shall see this shortly. This rhombic tricontahedron and icosahedron have their face and then their edge, respectively, coplanar with a cube that is 2 phi in edge. That's 2 times 1.618 or 3.236068. So this cuboctahedron is larger than the cuboctahedron in the jitterbug. This cuboctahedron, we'll get into that volume in a second. Let's turn this around. We have kind of a brain surgery here of the nesting polyhedra. Firstly, I want to point out that if you can isolate the red rhombuses, that's the rhombic tricontahedron. If you can isolate the orange lines, those are the edges of an icosahedron, the one that's in question. We also have an inner cuboctahedron, and that is inscribed within a cube as well. So I'm going to quick rattle off some volumetric relationships. Firstly, the inner cube here, which I'm poking right here at one of the corners, that has the cuboctahedron inscribed within it, it has an edge of just 2 units. Now I'm going to shift gears and say that that is a volume 8 cubic unit cube. It is inscribed within this rhombic tricontahedron, and the rhombic tricontahedron is 5 halves larger, 2.5 larger, so that would make it 20 cubic units. But we're talking Synergetics tetrahedral volumes, so I'll shift gears from that immediately back to tetrahedral units and say that the edge of this cube has 2 units long, which is the same as this edge of this icosahedron, but in tetravolumes it's going to be 6 times the square root of 2. Now, inscribed within the cube here is this smaller cuboctahedron. The cuboctahedron, when it is at the center points of each edge, it's a nice way to comprehend the cuboctahedron, it is always 5/6 the volume of that cube. Since we said the volume was 6 times the square root of 2, 5/6 of that is going to give the volume of 5 times the square root of 2. Oh, I forgot to go back and say one other thing, and that was the cube in tetravolumes has a 6 times the square root of 2 volume, and 5 halves of that would give the tricontahedron the volume of 15 times the square root of 2. Okay, so now I've just stated that the cuboctahedron had a volume of 5 times the square root of 2, exactly 1/3 in volume of the rhombic tricontahedron. That is an interesting relationship. Okay, now have we exhausted all the relationships enough? Just lastly, I'm going to point out that if you can see in this interior here, hopefully the pointer is making noise, there's a little shallow tetrahedron that lays on top of each icosahedral face, and that is a difference in volume between the rhombic tricontahedron and the icosahedron inscribed within it. if we say that the rhombic tricontahedron has a volume of 15 times the square root of 2, the icosahedron has a volume of 5 times 2 times the square root of 2. I'll say it again. 5 times the square 2. I'm saying it wrong. 5 times the square root of 2 times phi squared, and or 18.512295 is a volume. Quickly, I want to say something about T module volumes, and I also want to talk about this larger cuboctahedron. The T module or E module in Fuller's Synergetics is 1/120th of the rhombic tricontahedron. If we put a diagonal here, oops, there's always some little bugaboo, but anyway, and we projected one, that now that these 30 faces are divided into 4, that's 120 subdivisions, and they all project to the center origin. That would be the unit that I use as a unit of measure in volume, whereas the rhombic tricontahedron has 120 of what we call E3 modules, because it's a supersized rhombic tricontahedron, meaning that it's phi scale larger than the 5+ volume rhombic tricontahedron that is mentioned in Synergetics in relation to the volume 5 rhombic tricontahedron, from where the T modules derive, and the E module is slightly larger. And then if you scale that E module rhombic tricontahedron by phi, you get the what we call the supersized rhombic tricontahedron at 15 times the square root of 2. Okay, now I've mentioned that the cuboctahedron is 1/3 the volume of the rhombic tricontahedron. I also said that this icosahedron inside here is well, let me just say with the cuboctahedron, that being 1/3, it's going to be 40 E modules, E3 modules. 3 meaning powered by to the 3rd power phi. It's been scaled by phi. Okay, now the icosahedron is going to be 100 E3 plus 20 E0, because it's the straight E module. So that is the volume of the icosahedron in E module volumes. It's slightly smaller than the rhombic tricontahedron. Okay, this larger cuboctahedron is phi scaled larger, so it is also 5 times the square root of 2 times phi to the 3rd power. It ends up being 160 E3 modules plus 40 e to the 0 modules. Interestingly, if we subtract, no, let me say that differently. If we take we'll take the difference between the larger and the smaller cuboctahedron, and it's 160 E3 plus 40 e to the 0 minus 40 E3, we get 120 E3 and 40 E0 modules. So then if we divide that in half, we get 60 E3 modules plus 20 e to the 0 modules. If we add that to our smaller cuboctahedron, we get the volume of the icosahedron at 100 E3 and 20 e to the 0. And if we take it away from the larger cuboctahedron, the same 60 E3 and 20 e to the 0, we get the icosahedron volume. That took me a little while to say all that. I do have a couple other models now I want to show you. This here is like another way to understand the icosahedron is that it's actually a skewed inside of a tetrahedron where it has 4 coplanar faces. What's interesting is that these lines that define the triangle are the cut line if you're going to scale the tetrahedron into 5 volume increments. So in this case, there's a 3rd cuboctahedron, which is kind of hard to see in this morass of lines. So I just first wanted to show how it was derived out of this larger tetrahedron. If the icosahedron has an edge of 2, then the large tetrahedron has an edge of 2 times phi squared times square root of 2. So then there's also, I guess I should try to highlight that there's a coplanar triangle to the icosahedron triangle, which defines a cuboctahedron that has an edge, and that's the triangle sticking out because they're kind of canted to each other, that has an edge of phi square root of 2 times square root of 2. I said that wrong. Phi to the second power times square root of 2 over 2, which is an interesting number because it's 1.8155, which is the volume of the icosahedron actually in tetra units divided by 10. It's just an odd occurrence that I haven't fully figured out, but there is a relationship. So lastly, I'm going to show you another nesting here. And basically I have all 3 of those cuboctahedra. The 1/3 of the rhombic trichontahedron one here, the phi scaled one here, and then I have the one that I just described. It's coplanar. Its faces are coplanar with the icosahedron. You can see that if you look right in here. I just turned it around. Okay, so anyway, where are you? Of note, I had earlier said that the icosahedron was kind of the midway point volumetrically between the inner cuboctahedron and this larger cuboctahedron. And now I have to state this as well. None of these cuboctahedra that I'm talking about are the edge 2 VE. That is where this orange icosahedron is jitterbugged from. So that shows that this work is incomplete. But of note, the icosahedron inside is halfway volume between the outer cuboctahedron and the inner cuboctahedron. And if you look at this edge here to here, this cuboctahedron that's coplanar that was derived from that larger triangle, that's the midway point. So the volumes aren't matched up as far as the 3 cuboctahedron, but this icosahedron is the volumetric midway point, and this edge is the linear midway point. Okay, that's enough of that. Thank you.